Okay, let's talk about what we do after we have information from our data table. And so basically, how can we analyze this data and how can we graph it? Because through analyzing our data and putting it into graphs, we're able to truly analyze what happened in our experiment. Let's talk about three basic graphs. So the first one that we have is a bar graph. A bar graph is going to be used when we have ordered pairs that are compared in a discrete manner. So if you're comparing something like the brand of paper towels or the brand of chips, things that aren't necessarily number related and don't get counted in a continuous pattern. So the easiest way that I like to remember this is when you're looking at something that has a number versus the name of something. So something numerical, how many of something versus the name, not number versus number. So we have your independent variable. That is something that is like all text, numbers that represent something, sample 1, sample 2, brand of paper towel, brand of paper, brand of chips, something like that. And then the independent variable could also be something that is not a measurement, so something like colors. Okay, the second type of graph that is probably our most popular type of graph that we use is a line graph. We use line graphs when different measurements of the same item are going to be recorded over time. So a measurement that is continuous over time. So an easy way to remember that is number versus number. When you look at your independent and dependent variable, are you dealing primarily with numbers? So a couple of examples that are the easiest to remember are time or temperature. If you're dealing with time or temperature, those are measurements that are continuous. Temperature is continuous measurement, so you would see those sorts of things graphed as a line. Those aren't the only two things that we can graph in a line, but those are the most common ones that you will see us use throughout this year. So in both bar and line graphs, we've got our independent variable and the unit that will be located on the x-axis, and our dependent variable as well as its unit will be located on the y-axis. So an easy way to remember what axis this information belongs on is to use the acronym DRY mix. So DRY stands for the dependent responding y-axis, because it's the dependent variable that is responding to the independent variable, so the manipulated independent x-axis, and that would be your dry mix. So looking back at this example that we've looked at when we studied tables, we could take all of this information and put it onto a graph. And the first way that we can graph this is just looking at the trials. So you've got trials, 3 different trials, and we have that's represented down here, and then we have the mass of the tomatoes down to the left on the y-axis, and we are showing this each different trial. We ran 3 trials in this experiment, and then we've got our 4 different fertilizers, so we could see the outcome just by graphing it in this manner. And this can tell us a lot of information as we analyze our data. We can also just graph or create a second graph that shows us the average of the 3 trials, because we want to look at, however many trials that we do, and ultimately, average that together and see, okay, really which fertilizer was best for us to use to grow our tomatoes. Now, I would say that you should include both graphs, that I would include not only this graph of my trials, all my trials together, but I would also include the average, because that way when you go to analyze your data, you have enough evidence seen right there by the person that's reading your lab report, or by whoever is looking at the data, and can clearly tell exactly what you're analyzing and what your results are. And this kind of gives you that proof. And notice the reason why we used a bar graph in this case is because we're dealing with a number versus name, right? This is our number over here, and we've got names down here. Fertilizers are not, we can't count the fertilizer. We obviously will have a certain amount that we use, but technically we are comparing the brand of fertilizer, the 4 brands, Z, W, Y, or X, against the mass of the tomato and how heavy those tomatoes get over a certain period of time. Okay, let's look at another example, an example of a line graph. So the data in the next graph was collected on plant growth over a 7-month period. So we're looking at time, and this is continuous time. We start from one point in the year and we end 7 months later. And they measured the height of the plant within centimeters. So right here, the 7-month period is going to be our independent variable because we are the ones choosing, right? This is what we can manipulate. We are choosing how long we're going to measure this for. And the height of the plants is something that we don't directly control, right? It is what is going to be seen according to what happens with that independent variable and what we decide to do. So here's our table. And we have on the left-hand side our independent variable, and it corresponds to the right-hand side, the dependent variable. So right here, the first month, there was no growth, and those are the corresponding ordered pairs. The second month, we had 23 inches, the third month, 48, etc. So these are the corresponding pairs. They match up, and they correspond together. And lastly, before we move on, is look at the title, right? We're dealing with plant growth over time. We're dealing with a title that has both the independent and the dependent variable listed. It doesn't just say table number 1. So this gives us really good information about what we're looking at. Okay. So here's how we graph it. We would graph it as a line because, like I said before, we're dealing with numbers versus numbers, and we can see over time, which is our independent variable on the x-axis, that the plant has actually increased in its height. And in this case, we have a positive correlation because as time increases, so does the height of the plant. So a few things with line graphs: make sure that you label every axis, your y and your x axis, and you give the units. If you look back at this graph, I have my units, right? I have the time, which is given in months in this case, and we have our unit of centimeters. Okay, all graphs are going to start with the origin of 0, 0. We never want to have our starting point be, this should be 0, 0 right here. This shouldn't be starting at 0 for the y-axis, but then it starts at 20 for the x-axis. It's not accurate. And you can use what we call, it's kind of like a squiggle line, or what we call a break in the graph. So maybe your data doesn't start until you get to 1,000, right? So you'll maybe have 1 there, 2, okay, etc. But maybe you don't want to start marking it from here, at 10 or at 0, right? That's too much. So what you can do is put that break in there, and then the very first number that you count would start you at 1,000, okay? But what you have to know is you can't graph anything below this point. So you would have to, and naturally your graph would probably start from up here, right? You can't graph anything below because technically you didn't measure anything in that portion of the y-axis. That's why you put the break there. Okay, and then we have a couple things that may come up as you're analyzing your data. If you are taking a look at some information on your line, right, you'll have some points that you drew, and you drew the line amongst your points, okay? You can actually kind of do a prediction and you may be asked to make a prediction of something that happens out here. So let's just say, we're looking at information and we want to know what happens on the 12th month, right? We're looking at time, and this ends up, we want to determine and predict what's going to happen at the 12th month. Well, we can see that there is some sort of correlation, right? And if I continue, it's not quite accurate, sorry. Anyways, if you can predict what happens at the 12th month, but because we did not measure technically measure this point, that's why it's hollow. Those points that are not hollow are called interpolated because we actually measured them. They are solid points. These things we actually measured in our experiment. This point we did not measure. We can predict it, but we didn't measure it, and so it's a hollow point, and we call it an extrapolated point. So if you're asked within your questions or your analysis to make predictions that happen beyond something that you've measured, you have to add it to your graph, and it has to be something that is hollow. If it's not hollow and it's a solid point, that means that you didn't, that you measured it, and technically you did not. And also, something I did totally wrong is technically those extrapolated points should be dotted. So let me redraw this for you. Technically, we want to make a dotted line that carries out to that extrapolated point. So it'll look something like, it's really rough draft, but something like that. Okay, this again is something that we did not measure right here. So we signify it with the dashed lines and a hollow point. So if you have data that has a definite linear connection, you want to draw a best fit line. Otherwise, you'll connect the dots. Don't draw both types of lines. So let's just say you have data that looks just, pretty, sorry, those are like squiggles, pretty correlated, right? Well, you can take your ruler and you can go ahead and draw a best fit line because in general, your correlation was pretty positive. But what if you get data that is not as positively correlated? Maybe it's something sort of like this. Okay? This one's a little bit hard to see the trend, so what we would do is we would just connect the dots. But do not try to draw both. Don't draw, connect the dots and then try to draw, something that is like what you feel is best fit. This is incorrect. Okay? And then the last type of graph is a pie chart. The only time we use pie charts is when we are dealing with the something on a whole. Something when we're looking at the entirety of something. Looking at percentages is the easiest way to identify if we need to use a pie chart, but we're looking at pieces of a whole. So, for example, maybe we need to look at how many species of whales exist, in one of our oceans, and how many are there. So ultimately, we would be looking at the percentage of species of whales in a given area. So we would do some research. We would find what type of whales there are in that area. We'd have our list, and then we would be able to tag and count how many whales there are in that given area. And then after that, we can actually calculate the percentage of the population. So we can look at whales as a whole, right? And we can look at how many whales are there of the minke whale, the blue whale, the gray whale, etc. We can get a percentage, and the percentage should always equal 100% because we are talking about something on the whole. Okay, so after you were able to calculate that information, this type of information you would be able to graph as a pie chart. And so you could see right there we have percentages of the species of whales per, wherever this data is from, per given area. And those numbers would need to equal to 100%, and if they don't, then you've probably miscalculated something within your percentages.